Hello guys, welcome back to another video. Today we are going to be talking about the magnetic force acting on a current carrying wire in an external magnetic field. In order to do so, let's imagine the following situation. So we have some sort of an external magnetic field. This field was not created by the wire. So maybe there's a north and south magnet up and down here, or there's another source of a region of a magnetic field, but it's really important this is not a field created by the wire. And we place a piece of wire between two magnets in an external magnetic field. Let's see what happens. In our first instance, let's presume that there is no current in the wire. So there's no current, we just place a wire in between the poles of, let's say, a couple of magnets between north and south, and we wait and see what happens. And lo and behold, absolutely nothing happens. So if there's no current, I'm going to say over here, nothing particularly interesting happens. So nothing happens. Let's see what will happen if we had some current going through this wire. Okay, maybe not quite so much current, but let's have just a little bit of a cell with just a few volts, and let's connect that to this wire. And if that's the case, those electrons are going to get moving. They're moving in the opposite direction to conventional current, by the way, but because this is the positive and this is the negative terminal, the current will be going in the direction as shown, which in this case is counterclockwise. Anyhow, if we have current going through this wire, we will see something magical. There will be a force suddenly acting on this wire. In fact, the wire will experience a force upwards and is going to move upwards. Suddenly, there is a connection between the electricity and magnetism. The magnitude of this force experienced by the wire is given by the famous equation F is equal to Bill sine theta. F in this case is the magnitude of the magnetic force, so we can just write over here that this over here is our magnetic force, which is acting on that piece of wire, and we're going to be measuring that in newtons. B is a brand new quantity to us, and this is known as magnetic flux density. So magnetic flux density. I know it sounds like something taken out of Star Trek, the magnetic flux density, but it is an incredibly important quantity for magnetic fields. You can think of it as an equivalent of the strength of the magnetic field, and this is measured in Teslas, just like the car. And 1 Tesla, by the way, is normally a huge amount of magnetic flux density. It's comparable to the magnetic flux density of something like an MRI machine. So it's a very dangerous one. So most of the magnetic flux densities that we're going to be dealing with are going to be of the order of milliteslas. I is the current through the wire. So the current measured in amps, as we know. L is going to be the length of the wire, measured in meters, of course, and sine of the angle is going to be the angle between the wire and the field. And because it's the sine of that quantity, sine of theta will be dimensionless. Right, well, let's have a look. When is this magnetic force a maximum? The equation that we've just introduced is that F is equal to Bill sine theta. From pure mathematics, we know that the sine of 90 degrees is equal to 1, which will turn our equation into a maximum being that F is equal to B times I times L. And in fact, chances are this is the form of the equation that you guys would have studied at GCSE level, which is one particular case when the angle between the field lines and the current is 90 degrees. Notice that there are a total of 4 directions in which the field could be orientated. For instance, if the field was going up, it'll be perpendicular to the current. If the field was going down, it will also be perpendicular to the current. However, let's think in 3D. If the field is going into the board, it will also be at 90 degrees to this wire, or if it was going out of the board, it will also be at 90 degrees to this wire. You can kind of think of it, let's see if I can sort of draw in sort of 3D. You have to imagine this kind of coming in or out of the board. So it could either be going up or down or in and out of the board. Now, when is the force actually zero? Additionally, we can imagine the field being parallel to this piece of wire, and if that's the case, the sine of the angle is going to be zero because the angle between them would be 0 degrees. So in this case, when they're parallel, the force will be equal to B times I times L times the sine of, let's say, 0 degrees, which is actually equal to 0. So this means that there is no force which is acting on this piece of wire. Okay, folks, so just to summarize, we've had a look at a piece of wire which is an external magnetic field, and initially when there was no current, nothing happened. However, notice what we've actually done. We've managed to convert some electrical energy into some kinetic energy, because as soon as we ran some current into the wire, there was actually a force acting on it. Well, this is the invention of the electric motor. How amazing is that? Okay, folks, well, hopefully you've enjoyed this video, and if you have found this video useful, thank you very much for watching, and I'll see you in the next one.